Swayam Prabha. Digital India. Educated India.
Today we are going to discuss some examples on the simplex method. In the last class, if you recall, we have discussed the simplex method, and I have taken a particular problem, and using that problem I have explained the simplex method to you. Now what I thought that maybe we can take more examples and solve those problems by using the simplex method and explain that methodology once again so that it becomes more clear to all of you. So with that thought in mind, let us take certain examples and solve by the simplex method. So this is a problem. Let us take, it's a very simple problem. Let us say the original problem is maximize z equal to 2x1 plus 3x2 subject to x1 less than equal to 4, x2 less than equal to 4, and x1 plus x2 less than equal to 6. And apart from that, we also have some non-negativity constraints, that is x1 greater than equal to 0 and x2 greater than equal to 0. So as the problem is very clear that it's a maximization problem and there are three different constraints, and in order to get the augment, we have to then take some slack variables. Let us say that three slack variables we have to take: x3, x4 and x5. So x1 plus x3 equal to 4, x2 plus x4 equal to 4, and x1 plus x2 plus x5 equal to 6. And the non-negativity constraints will be x1 greater than equal to 0, x2 greater than equal to 0, x3 greater than equal to 0, x4 and x5 both are greater than equal to 0. One thing you observe that an objective function is also written. What you observe is that after writing the constraint in this manner, all the inequalities have now become equality. That is the first thing to observe. The second thing to observe is that these variables x3, x4 and x5, which are the slack variables which are added to make the augmented problem from the original problem, they are occurring in only one equation. Like x3 is occurring only in the first equation with a coefficient of 1. x4 is occurring only in the second equation with a coefficient of 1. x5 is occurring only in the third equation with a coefficient of 1. And these x3, x4, x5 together, they form an unity matrix. Why unity matrix? 1, 0, 0, 0, 1, 0, and 0, 0, 1. So when that happens, that means the three variables which are called the slack variables, and we shall call them basic variables. Why we shall call them basic variables, I'll explain a little later. They will form what is known as an unity matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that matrix, because it is in that form, that is why we are saying these equations are in canonical form. And this canonical form is very important. In the simplex method, what we do, we express this in the form of a table. And if you look at, there are 5 unknowns and there are 3 equations. So only, 3 can be solved. Those which can be solved are called basic variables. Those which are put to zeros, because other 2 variables we have to put to zeros, they are called the non-basic variables. Now you may be thinking that there could be other solutions also, but we are not interested in those other solutions. We are only interested in these kind of solutions which are called basic solutions. Why they are basic solutions? Because at a time 2 of the variables are zeros. In a sense, they represent some corner points. Graphically, I shall show you that also. So what we get is at any point the equations are written in such a manner that there are some basic variables. The basic variables occur in only one equation with a coefficient of 1, so that together all the basic variables forms an unity matrix, and that we call as the canonical form. And this canonical form is very important to we have to maintain that as we move in the simplex from one table to the other. So as one basic variable leaves the basis and one non-basic variable joins the basis, so now we have another three variables, and we have to again restore the canonical form by suitable operations. That is what we exactly do in the simplex method. So let us now see that why it is the those basic solutions are important. Already I have explained in other classes, but once more let us see it. You see, are the different constraints, that is x1 equal to 4, x2 equal to 4, and x1 plus x2 equal to 6. Now, if you put, those slack variables, then x1 plus x3 equal to 4, x2 plus x4 equal to 4, and x1 plus x2 plus x5 equal to 6. So what happened along this line? We can say x4 equal to 0. Along this line, x3 equal to 0. Along this line, x5 equal to 0. Along this line, x1 equal to 0, which is the x2 axis, and along this line, which is the x1 axis, x2 equal to 0. So basically, if you see that every corner point is, two variables are zeros. So at origin, x1 equal to 0 and x2 equal to 0. At A, what are the variables that are 0? x2 equal to 0 and x3 equal to 0, because x1 equal to 4, so x3 will be equal to 0. But if you go back to the original problem, they are not equalities, they are actually inequalities. So since they are inequalities, that x1 less than equal to 4 is this side, x2 less than equal to 4 is this side, and x1 plus x2 less than equal to 6 is this side. So that is our common solution space, and we are not interested in points which are within the solution space. We are only interested in the points which are the corner points. And we have already explained earlier that why the optimal solution is one of the corner point solutions. Additionally, these are linear programming problems which are having a single peak. Since they are single peak, we can use a hill climbing method, and that hill climbing method is from point O, we go to another point, say A, and then go to another point E. Like this, we keep going from one point to the another point. And if we get a point, I don't know which one, suppose in this case D is the point which is the best possible point. So suppose we reach D, then we see that all the points which are feasible, that is point B, point E, or point C, which is infeasible point G, which is an infeasible point. So all the feasible points, that is B and E, which are near to D, they are all lower in value compared to this point D. So what really happens? You are doing a hill climbing with a single peak, and we find a point that whichever direction you look, it is lower. That means that is the peak. So that is the essential idea here, that if we get a point, we don't have to evaluate all the points. In graphical method, we are evaluating all the points. In simplex, we don't have to do that. Maybe we can go from first to the point O, and thereafter, we can go to a more profitable point, maybe point B, and then from point B we go to point D, and that's all. We don't have to evaluate other points, because once we reach D, we find there is nowhere to go, which improves that means no more hill climbing is possible. That means we have reached the peak. So that is essentially what is the simplex method. Begin at the origin, evaluate the point, see that it is in canonical form, then move to another point, check that the canonical form is maintained, and like this, we continue. So this is the graphical solution. It also shows that why in the simplex method we don't need any in-between points. We only need the corner points to be represented, and the corner points are found by putting some variables to zeros. Those are non-basic variable. Like in point O, x1 and x2 are put to zeros. So there are values for x3, x4 and x5. So once again, this I have shown earlier, but anyway, I repeat that George Bernard Danzig, he developed the simplex algorithm, and starting from an initial canonical table U, the algorithm moves from one basic feasible solution to another till the optimal solution is found. Now, every W should be in a canonical form, that is, the basic variables must form an unity matrix when taken in a particular order. So when one variable leaves the basis and one non-basic variable enters the basis, we have got another set of basic variables which should be again restored to the canonical form, and that is done by the pivot operation. A non-zero pivot element from the non-basic column is converted to 1, while the other entries in the row are converted to 0. Uh, not in the row, in the column. The variable of this column then become a basic variable, and the variable in the row of the pivot element becomes a non-basic. The choice of the pivot element is on the basis of optimality as well as feasibility consideration. So this is our simplex fast table. So let us look at the simplex fast table carefully. This is x3, x4, x5, they are the basic variables. So you can see that they have formed an unity matrix. Right? This is an important thing to note, that the variables there in the basis, will form an unity matrix and the canonical form is maintained. After that, the other two variables x1 and x2, they will have their coefficient values, that is 1, 0, 0, 1 and 1, 1, which are the whatever coefficients we have. And then here we write the Cj, that means the profit coefficient row. Here Cj are 2 and 3, 2 for x1 and 3 for x2. Similarly, on the other side, we write the Ci, so which are 0, 0, 0. And thereafter, we compute the Cj minus Zj values, and those values are 2 and 3 respectively, because to bring unit of x1 into the basis, we have to give up 1 unit of x3, 0 unit of x4, and 1 unit of x5. So when we give up these 1 unit of x3 and 0 unit of x4 and 1 unit of x5, the cost of that is 1 into 0 plus 0 into 0 plus 1 into 0. That means 0. So that means lost profit, that is called Zj, will be equal to 0 per unit for bringing 1 unit of x1 into the basis. Since profit for 1 unit is 2, the net profit per unit Cj minus Zj would be 2. Alright, on similar basis for x2, that value would be equal to 3. So that is about our simplex fast table. Once we have written that basic variables are x3, x4 and x5, non-basic variables are x1 and x2, and Ci and Cj are the profit coefficients. Observe the unity matrix formed by the variables in the basis in the coefficient matrix. This table is in canonical form. So these are the things, and this is our augmented problem. Isn't it? So this much is very clear to all of you, and we have already explained this in with another problem in the previous class. So this is another repeat of that thing with another problem. So I am sure you have understood this. All right. Now Cj minus Zj and Zj values are computed. Zj is cost of bringing 1 unit of into the basis, and Cj minus Zj is net profit for bringing 1 unit of non-basic variable into the basis. Once again, let us understand this. The x3, x4 and x5, they are our resources. How much of these resources are available? X3 is available quantity 4, x4 is available quantity 4, x5 is available quantity 6. Now, to make 1 unit of x1, we need 1 unit of x3, 0 unit of x4, and 1 unit of x5. Currently, our solution is origin, that is x1 0, x2 0, x3 4, x4 4, and x5 6. That is what is shown by the first simplex table. Now, suppose you make x1 equal to 1. If x1 is equal to 1, x2 remains 0, then what should be the value of x3, x4, and x5? Because you have already made 1 unit of x1, that would require 1 unit of x3, 0 unit of x4, and 1 unit of x5. So the new solution will be x1 equal to 1, x2 equal to 0, x3 equal to 3, x4 equal to 4, and x5 equal to 5. What has happened? The 1 unit of x3, 0 unit of x4, and 1 unit of x5 has been given away. Now, since that much resource is taken away, it will make an impact in the profit. But fortunately, there is no profit coefficient values with these resources x3, x4, x5. So those cost is 0. So that means the lost profit in this case is 0. All right. And since Cj value is 2, so 2 minus 0 will be 2. So this is how that lost profit and net profit per unit or net profit for bringing 1 unit of non-basic variable into the basis can actually be computed. All right, so this is how we have got the Cj minus Zj values. Now, when it comes to simplex, there are two considerations. One is the optimality consideration, another is the feasibility consideration. So between x1 and x2, we find that the x2 is a more profitable direction. That means if we move towards x2, we are going to make more profit. So we move towards the x2 direction. So look at this graph once again. This is the x2 direction because this is the x1 axis, this is the x2 axis. Along the x2 axis, x1 equal to 0. So we have seen that because the profit coefficients, Cj minus Zj, next what you call the net profit per unit is higher for x2. So from the beginning point O, which is represented by the simplex fast table, if we move towards A compared to if we move towards B, the moving towards B is more profitable, is it not? Because Cj minus Zj value is higher. So question is, how much can you move? Now, can you go all the way to point B or can you go all the way to point C? You see, the question is that we cannot go all the way to point C because point C is a better point, obviously higher value of x2, but at that point there is no feasibility. So feasibility is not there. So one big consideration is the optimality. Moving towards B is going towards a better solution, but also we have to see the feasibility. In fact, there are 3 points. Other point is not seen. The B is the point where x2 equal to 4, that line, and C is the point when x1 plus x2 equal to 6, that line. And you see these x2 equal to x2 axis, that is x1 equal to 0 and x1 equal to 4. They will not meet because they are parallel to each other. Assume they will meet at infinity. So there is a third point which is infinity. So from O we can go to B, we can go to C, and we can go to infinity. All right, but we should go to B because that is where the bottleneck resource x2 equal to 4 is going to be there. So maximum number that we can make is 4 only. All right, so having said that, so these are certain important consideration. So first of all, the optimal direction, that means x2 should now come into the basis. All right, so that is the first thing we understand, that yes, x2 should now come into the basis. So here our choice is made because it is higher value of Cj minus Zj, and Cj minus Zj value is maximum for the non-basic variable x2. Hence, x2 is the entering variable into the basis. And Cj minus Zj, that is net profit for bringing 1 unit of non-basic variable into the basis. So we have x2 now coming into the basis. So next question is, which variable should be the leaving variable? As x2 comes into the basis, which variable should leave? Should it be the x3 or x4 or x5, right? So that we have to decide. Now look here, which one is the bottleneck resource that we have to work out. To make 1 unit of x2, we make need 0 unit of x3, 1 unit of x4 and 1 unit of x5. Now we have 4 units of x3, 4 units of x4 and 6 units of x5. Suppose we make 6. What is going to happen? 6 into 0, we need 0 quantity of x3. How many are available? 4. So it is not a constraint. How many of x4 we need? 6 into 1, 6. How much is available? 4. So it will create a problem, right? Because we need 6 units of x4 and we have only 4 units of x4. With regard to x5, if we make 6, 6 into 1, 6, 6 are available, no issue. So what has happened? You see that we cannot make 6 units of x2. We have to make less. How much less? X4 will be the bottleneck resource because only 4 units are available. That means only 4 units of x2 can be made. How many resource will be required? 4 into 0 here, 4 into 1, 4, and this resource will be exhausted, and 4 into 1, 4, x5, so 2 more x5 units will remain. So from a preliminary consideration, it is very clearly seen that the bottleneck resource here is x4, right? So therefore x4 should be the leaving variable, right? So this is the consideration, and that consideration should be actually taken, and you don't have to worry about 4 divided by 0 is how much and all that. You have to understand how much are required and whether a certain resource is bottleneck resource or not. So this is exactly what is written here. X4 is the bottleneck or the critical resource and will be our choice of the leaving variable. So choice of the leaving variable from the basis. So x2 is the entering variable. To make 1 unit of x2, we need 0 unit of x3, 1 unit of x4 and 1 unit of x5, all 3 resources. We have available 4 units of x3, 4 units of x4 and 6 units of x5. All right. So we can thus make minimum of 4 by 0, 4 by 1 and 6 by 1 equal to 4 units of x2. That is maximum possible unit of x2 that we can make is only 4 units. So this is how we can calculate the feasibility. You can do the mathematics by simple divisions, or you can also try to understand it from the bottleneck resource point of view. So fine. So what we have done, we have been able to identify the leaving variable and the entering variable x2 and the leaving variable, that is x4. So both we have been able to identify. Now after we have been able to identify that, now we have to use this formula. So what is this formula? First of all, the key row values will be replaced by old values divided by the intersecting element. The key column values will be replaced by 1 in place of intersecting element and 0 in other places. And what is the formula to be used for other elements? New element equal to old element minus corresponding key row element into corresponding key column element divided by the intersecting element. Now why these formula are true? What is exactly happening out here? Basically, what is happening? We are first of all dividing this by the intersecting element. So what we get after, so here intersecting element is 1. So nothing much division would be occurring. So we can straightaway say that x2 plus x4 equal to 4. Isn't it that from this equation we can straightaway write x2 equal to plus x4 equal to 4. So therefore x2 is 4 minus x to the x4. In fact, 4 by intersecting element minus x4 by intersecting element, because if this is 1, if it had been 2 or something, then it would be divided by 2. So 4 by 1 minus x2 by 1. So that is the value minus, sorry, x4 by 1. That is the value of x2. Now that value of x2 we are now putting in this constraint. So what happens from here? X2 is eliminated. X2 is 0 anyway. Here x2 equal to 1, so x2 also gets eliminated from here. So if x2 is eliminated from two equations, so what is going to happen? Then this will be in canonical form, and this will take 0 1 0 form. All right, so precisely that is what is done. And when you do that, then these other elements will become, they will be obtained by using this kind of formula. All right, so now we use this formula and we try to get the next table. So what we do, see, this is our key row. The key row is now replaced by dividing every element by the intersecting element. So it will now become 4 0 1 0 1 0. All right, and the key column will now reduce to, which was x2 0 1 1. It will now become 1 0 0, sorry, 0 1 0. That is for x2. So now x3 x2 and x5, instead of x3 x4 and x5, they will now be in the basis. So they will also form the unity matrix in that order. So x3 1 0 0, x2 0 1 0, x5 0 0 1. Right, so we get the new canonical form between x3, x2 and x5, which will now form an unity matrix. All right, so we have that unity matrix formed by the new variables in the basis, and x1 and x4, they will be our non-basic variables. So those values have to be calculated. Now, how do you calculate? Let us say what will happen to this value 4. So you see 4 minus 4 into 0 by 1. Since the key row element is 0, anything you multiply and divide, no change will happen. So that means this row can be written as it is, right? 4 minus 4 into 0 by 1, 1 minus 0 into 0 by 1, 1 minus 0 into 0 by 1, 0 minus 1 into 0 by 1, and 0 minus 0 into 0 by 1. So no change in this column. So in this row. So it will become 4 1 0 1 0 0. The same thing will be repeated. The key row, already we know we have to divide everything by intersecting element. So it will become 4 0 1 0 1 0. Now what this 6 will become? 6 minus 4 into 1 by 1. So it is 2. This 1 will be 1 minus 1 into 0 by 1. So it is 1. This is already key column. So already it is evaluated. And this 0 will be 0 minus 1 into 0 by 1. So 0. This 0 will be 0 minus 1 into 1 by 1, so minus 1. This 1 will be 1 minus 1 into 0 by 1, so 1. In fact, a much better and simpler way is that don't bother about every calculation. First, you write the key column, that is 0 1 0, key row divided by the intersecting element, then the canonical form x3 1 0 0, x2 0 1 0, and x5 0 0 1. So only the remaining values of x1 and x4 are to be calculated. So those are actually only 4 numbers are to be calculated by this formula. All right. So that is how we have obtained the second table, and the second table is still not complete because we have to complete Zj and Cj minus Zj. We know the Cj minus Zj values are zeros for the basic variables. So there is no need to compute for the basic variables. That means not for x2, x3 or x5. So only for x1 and x4 we have to calculate. So what is the Zj for x1? you see it is 1 into 0 plus 0 into 3 plus 1 into 0. So Zj equal to 0. And already we know Cj is 2. So 2 minus 0, Cj minus Zj value would be 2. How much is for x4? 0 into 0, 1 into 3, that is 3, and minus 1 to 0, that is 0. So Zj will be 3. That means to make 1 unit of x4, you have to give up 1 unit of x2 and minus 1 units of x5. So x2, that would cost you 3 units. So Zj is 3. And 0 minus 3, Cj minus Zj is minus 3. So that is simplex second table. So basic variables now x3, x2 and x5. Non-basic variables are x1 and x4, which are shown in white. Observe the unity matrix formed by the variables in the basis of the coefficient matrix in that order. That means x3 100, x2 010, x5 001. Could you find that table is in canonical form? Yes, it is in canonical form. Note the order of the basic variable also. That means unity matrix will be formed by the variables in the basis when taken in this order. What is that order? X3, then x2 and then x5. So then we get the simplex second table. So then we compute the Cj minus Zj values, and the Cj minus Zj values recompute the Zj and Cj minus Zj for the non-basic variables. In the second table, these are x1 and x4 respectively, because for basic variables we know they are zeros, so we can straightaway write zeros, or we may not even write. Then Cj minus Zj value for the non-basic variables can be computed or calculated by the formula given above. So the formula is already known. That is, so they can also be calculated. See, that is what is being said here. They can be also calculated by this formula. So how can you do this formula? So old element minus corresponding key column into key row divided by the intersecting element. So 2 minus 3 into 0 by 1. So 2. And 0, 0 minus 3 into 1 by 1. So minus 3. So you can also calculate by this formula. Alright, so that way also you can compute the Cj minus Zj values. Alright, so or you can calculate Zj by the method I have already discussed, and then deduct from Cj. That way also you can do. So Cj minus Zj then will be 2 and minus 3 respectively. So that is what our second variable, second table is obtained. So entering variable should be from the optimality criteria. Cj minus Zj value is maximum for the non-basic variable x1. Not only that, it is a positive quantity. And if it is negative quantity, it will be not considered. It has to be a positive quantity, so that the net profit actually should go up if x1 comes into the basis. Hence, x1 is the entering variable in the basis. And Cj minus Zj, that is the net profit per unit for bringing 1 unit of non-basic variable into the basis. So x1 would be our entering variable. So now tell me, which one is going to be our bottleneck resource? X3, X2 or X5? Please think and try to tell me X3, X1 or X2 or X5, which one? You see, to make 1 unit of X1, we need 1 unit of X3, 0 unit of X4 and 1 unit of X5. So, is it clear that X5 is going to be our bottleneck resource? Because 4 by 1 is 4, 4 by 0 is infinity, and 2 by 1 is 2. So 2 is minimum. That means only 2 can be made. That means X5 will be the bottleneck resource. Yes or not? Suppose only 2 you make, then X5 will be exhausted. X2 will not be exhausted because only 0 units are required. And X3 also will not be exhausted. Only 2 units will be consumed. Another 2 will remain. So we see that x1 is the entering variable. To make 1 unit of x1, we need 1 unit of x3, 0 unit of x4, x2, and 1 unit of x5, all three resources. We have available 4 units of x3, 4 units of x2 and 2 units of x5. So we can thus make 4 by 1, 4 by 0 and 2 by 1 minimum of these, and it is 2 units of x1. That is the maximum possible number of x1 that we can make. So therefore we see that x5 will be the leaving variable. So x1 is the entering variable, x5 is the leaving variable. So x5 is the bottleneck or the critical resource and will be our choice of the leaving variable. Alright, so this much already we have understood, and we have also obtained those values. So now again we have to follow the formula, and through that formula we can again then obtain the simplex third table, right? So how to do that? Once again, the key row, this is our key row, everything should be divided by the intersecting element. Now intersecting element is 1 only, so therefore it will be same thing will be repeated. So but x5 will be replaced by x1. So in this case it is 2 1 0 0 minus 1 1. Then when it comes to the key column should be transformed to 0 0 1. Alright, so key column is taken care of, key row is taken care of. Then the basic variables, that is x3, x2, x1 are to be taken care of. So x3 1 0 0, x2 0 1 0 and x1 0 0 1. So unity matrix is obtained in that order, x3, x2, x1 in that order. So unity matrix is obtained and it is in the canonical form. So that is also seen that canonical form is maintained. Now what are the non-basic variables? X4 and x5. Out of that the key row is already taken care of. So these are the 4 values that we have to calculate. How to calculate? Look here, this is 0. So 0 minus 1 into 1 by 1. So 0 minus 1 into 1 by 1. So it will become plus 1. How much this 1 will become? 1 minus 1 into 0 by 1. So it remains 1 because of a 0 here. So anything with 0 becomes 0. So no change to the value. So 1 remains 1. Then what will happen to this 0? This 0 will be 0 minus 1 into 1 by 1. So it will be minus 1. And what about this 0? 0 minus 1 into 0 by 1. So it remains 0. So that's all. Not many thing are to calculate. So based on that, the third table is obtained. Alright, so third table is obtained, and we have to then compute the zj's and cj minus zj. We know that for basic variables they will be all zeros. Now for the non-basic variables only we have to calculate. One method is 1 into 0, 1 into 3, minus 1 into 2. So net zj is 1. And minus 1 into 0, 0 into 3, 2 into 1, zj is 2. So therefore cj minus zj will be 0 minus 1, that is minus 1, and 0 minus 2, that is minus 2. Or we can also compute directly from the formula, that is minus 3 minus 2 into minus 1 by 1, that is minus 3 plus 2 equal to minus 1. And this one would be 0 minus 2 into 1 by 1, so minus 2. So this is how we get the third table. An interesting thing to note, look at the third table. All the cj minus zj values are negative for a maximization problem. So it is a maximization problem and cj minus zj values are all negative, which means that to bring x4 or x5 into the basis, the profit is not going to go up, the profit is only going to decrease. Therefore, that this table already shows the optimum solution. So the simplex third table is our optimum table, and the value is x1 equal to 2 and x2 equal to 4, and therefore z should be equal to 16 because objective function 2x1 plus 3x2. So 2 into 2, 4 into 3. So z star will be 16. Yes or not? So what has happened really? This is the third table, and the second table, if you look at which represented x1 equal to 0 and x2 equal to 4. And in the third table, x1 equal to 2 and x2 equal to 4. So let's go back to that graph once again and quickly convince ourselves that this is exactly what is happening. So we started with the first table representing the origin, which is x1 equal to 0 and x2 equal to 0. The second table represented the point B, and at point B, we had 0 and 4, x1 equal to 0 and x2 equal to 4. And from B we have come to point D, and we now find x1 equal to 2 and x2 equal to 4 and z equal to 16. So that second table, actually third table, once we go from second table to the third table, the third table represents the optimum solution, because in moving in any direction doesn't improve the objective function, it only decreases it. Alright, so therefore, since it's a single peak hill and we are following a kind of hill climbing method, so that means we have already reached the top of the hill. That means the point D is our optimal point. Alright, so this is how these calculations are done, that we have the first table. From the first table, we find out the entering variable. From the entering variable, we find the leaving variable. We see the key row and the key column. Key row is divided by the intersecting element. Key column becomes an 0, 1, 0. That is so that that canonical form can be maintained. And the other elements are obtained by new element equal to old element minus corresponding key row element into corresponding key column element divided by the intersecting element. So that's what we do. And thereafter, that from the second table, then x4 is the leaving variable, x2 is the entering variable, and then we again use the formula, we get the third table, and from the second table, and then we find that this entering variable x1 and x5 is the leaving variable, and from there the third table is obtained by using the similar formula, and the third table is our optimal table, because all the Cj minus Zj values are negative in a maximization problem. In a minimization problem, the stopping criteria is all the Cj minus Zj value should be positive. But we shall discuss minimization problem later in much more detail. So as all the Cj minus Zj values are negative for a maximization problem, the optimal solution is obtained. Alright, so this is how these kind of problems are to be solved by the simplex algorithm. Now let us take a second example quickly, and the second example is we are having certain interesting thing to observe. Right. So let us say we have a linear programming problem. Maximize z equal to 28x1 plus 30x2 subject to 6x1 plus 3x2 less than equal to 18, 3x1 plus x2 less than equal to 8, 4x1 plus 5x2 less than equal to 30, and x1, x2 both are greater than equal to 0. So again, the augmented problem will require three more variables, slack variables, x3, x4, x5. So 6x1 plus 3x2 plus x3 equal to 18, 3x1 plus x2 plus x4 equal to 8, 4x1 plus 5x2 plus x5 equal to 30, and all the x1, x2, x3, x4, x5 they are greater than equal to 0. And the objective function 28x1 plus 30x2 plus 0x3 plus 0x4 plus 0x5. Alright, so this is our original problem and the augmented problem. So what we do next, we form the simplex fast table. So this is our simplex fast table, x3, x4, x5 as basis, because they are in canonical form. 18, 8 and 30, they are the values, and x1 and x2 coefficients are 6 and 3, 3 and 1, and 4 and 5, and then rest is canonical form. And here are the Cj values 28 and 30 and 0, 0, 0. So Cj minus Zj can be straight away calculated because they're all zeros. So Zj is 0. So Cj minus Zj is Cj minus 0. That means 28 and 30. So straight away we can write Cj minus Zj values. Entering variable should be x2 because it has got a higher Cj minus Zj. Alright, so x2 should be the entering variable. Now quickly, can you tell why x3 is the bottleneck variable? Just think a little bit and tell me why x3 is the leaving variable in this case. Think a little bit, just spend a minute. Just look at the values. See, also note that to make 1 unit of x2, you need 3 units of x3, 1 unit of x4 and 5 units of x5. So how many can you make? You can make 18 by 3 equal to 6, 8 by 1 equal to 8 and 30 by 5 equal to 6. But there is a tie. Can you see that there is a tie? Note that there is a tie in the leaving variable. Both x3 and x5 are candidates. Now which one we should choose? Because this is a dilemma. We have a tie and we do not know whether we have to choose x3 or we have to choose x5. So let us choose x3 to begin with. Suppose we choose x3 as the leaving variable. So when we choose x3 as the leaving variable, this is what we are going to get. First we have to compute the key row. The intersecting element is 3. So we can divide every element by 3 and we can replace x3 by x2 because x2 comes into the basis, x3 goes out. So x2 and then 18 by 3 equal to 6, 6 by 3 equal to 2, 3 by 3 equal to 1, 1 by 3, 1 by 3 and they are 0, 0. Alright, so this is the key row element. Then the key column should be transformed to 1, 0, 0. So x2 column will be now 1, 0, 0. And x4 and x5 they are also in the basis. So 0, 1, 0 and 0, 0, 1. So look at the canonical form. The unity matrix is formed by the variables in the basis x2, x4 and x5. So that is 1, 0, 0, 0, 1, 0 and 0, 0, 1. And remaining coefficients have to be calculated with the use of formula. So this 8 will be 8 minus 18 into 1 by 3, that is 8 minus 6 equal to 2. This 30 will become 30 minus 18 into 5 by 3, that means 30 by 30 equal to 0. This 3 will become 3 minus 6 into 1 by 3, so 1. This 4 will become 4 minus 5 into 6 by 3, that means 4 minus 10 equal to minus 6. Similarly, for x3 we can get 1 by 3, minus 1 by 3 and minus 5 by 3. And x2 coefficient 30 we can write. So therefore the Cj minus Zj also can be computed by formula 28 minus 30 into 6 by 3. So 28 minus 60 equal to minus 32. And for x3 earlier it was 0. So 0 minus 30 by 1 by 3. So minus 10. So Cj minus Zj values are also minus 10 and minus 32. Both are negative in a maximization problem. So optimum solution is already obtained. So what is the optimal solution? Basis x2 equal to 6, x4 equal to 2 and x5 equal to 0. So therefore z star equal to 180. So what is the optimum solution? X1 equal to 0 and x2 equal to 6, that is 180. So already we got the optimum solution, but one very interesting thing to note that there is a 0 in the basis, right? So when there is a 0 in the basis, we call the optimum solution is degenerate because there is a 0 value in the basis. So these degenerate solutions we shall again discuss in detail when we talk about the special cases in linear programming. All right. So our next topic after simplex will be special cases in linear programming. At that time, we shall discuss what are degenerate solutions and what are their significance in greater detail. Now, before we end, let us also see, suppose in the second table, there was a tie. So we have chosen the first one, that is x3 as the leaving variable. But suppose we would have chosen x5 as the leaving variable, then what would have happened? All right. So if x5 would have been the leaving variable, so in this case things will be slightly different. You will see then that 30 minus, so x2 comes into the basis. So we have 6 here because the 5 is the intersecting element. So first of all, key row will be 30 by 6 equal to 30 by 5 equal to 6, 4 by 5 equal to 4 by 5, 5 by 5 equal to 1, 0 by 5 0, 0 by 5 0, and 1 by 5, that is 1 by 5. And the key column x2 should be transformed to 0 0 1. Then the between x3, x4 and x2 there should be canonical form. So 1 0 0, 0 1 0 and 0 0 1. So canonical form is also written. And thereafter the remaining elements can be calculated. This 6 will now become 6 minus 4 into 3 by 5. So 6 minus 12 by 5, so 18 by 5. This 3 will be 3 minus 4 by 5. That means 15 by 5 minus 4 by 5, so 11 by 5. Similarly, you can also compute the x5 coefficients. All right. And then we can compute the Cj minus Zj, 28 minus 30 into 4 by 5. So 28 minus 24, that is equal to 4. And this value would be 0 minus 30 by 5, so minus 6. Now interestingly, you see this is not the optimum table. We don't get the optimum table. So in this case, x1 will come into the basis. All right. And which one should be leaving variable? Which one is the critical? So we shall see that later. So we do not get the optimum solution at the second table with x5 leaving. So with x3 leaving, the second table itself become optimal, but it is not so. It has not happened in this case. A positive Cj minus Zj value for x1 suggests that x1 will now come into the basis. So which one is the bottleneck resource? X3 is becoming the bottleneck resource. So why x3 is the bottleneck resource? Because very easy to see that value is 0 and coefficient is 18 by 5. So we have nothing available. Since nothing is available, that is actually, and we require something to make anything. So that means we cannot really make anything, right? So x1 may come into the basis, but with a 0 value. So there is no improvement in the objective function. All right. So you see what has happened, that x1 comes into the basis, but with a 0 value only. That means it is not going to contribute in any manner to the objective function value, because earlier also the solution was x1 equal to 0, x2 equal to 6. Now also the solution is x1 equal to 0 and x2 equal to 6. So very interesting thing has happened really, and that is the basis for understanding of the degeneracy, right? So that is what, there is a degeneracy, there is a 0 value in the basis, and there is some specific understanding about it. So what is that understanding? We shall see a little later when we talk about degeneracy. But at this point, let us complete the problem. This is going to be our key row. So in this key row, the intersecting element is 18 by 5. So we have to divide each element by that. So it will become 0, then 1, then 0, 1 will become 5 by 18, 0 remains 0, and minus 3 by 5 becomes minus 1 by 6. And then the canonical form is obtained by x1, x4 and x2. So x1 1 0 0, x4 0 1 0 and x2 0 1 0 0 1. So we can write the canonical form. And already the key row column we have written, and key column is also taken care of. So the remaining non-basic variables, that is x3 and x5 coefficients, we have to compute. So these these x3 value, these 0, so 0 minus 11 by 5 into 1 by 18 by 5. So like this the computation have to continue, and we get minus 11 by 18, minus 2 by 9, 1 by 6 and 1 by 3. And then we have to compute the Cj minus Zj also. So this was 0 earlier. So it will be 0 minus 4 into 1 by 18 by 5. So minus 10 by 9. And this was minus 6. So minus 6 minus 4 into minus 3 by 5 by 18 by 5. So minus 16 by 3. Now both are negative. That means the optimal solution is obtained. So what is the optimal solution now? The optimal solution is the basis value is x1 equal to 0, x4 equal to 2 and x2 equal to 6. But since the original problem has got only x1 and x2, so the solution we get is x1 equal to 0 and x2 equal to 6. So that is z equal to 180. So interestingly, if you observe from the previous table, something very interesting happens. Now in the second table itself, we got a solution x1 equal to 0, x2 equal to 6. And in the final table also x1 equal to 0 and x2 equal to 6. So although we have made one more iteration, yes, we have made more iterations, but by making more iterations, we have really not improved our solution. Is it not? The solution has not improved. The solution remains the same, but we have iterated. That is because a zero value has come into the basis. Because the zero value has come into the basis, it has not improved our optimum solution value. So that could be when there is degeneracy, there is a zero value in the basis, and it occurs when there is a tie, and there will be a tie, and depending on which one you choose, you might get different solving mechanisms, but end of the day you get the same solution. Is it not? So anyhow, so what we have done, we have solved two problems by simplex method, so that further examples we have obtained, and our understanding of simplex method has become little better. Now, however, there are certain other very important and interesting observations about the simplex table, specifically the shadow prices and the B inverse matrices. So those things we shall discuss in our next lecture, and in the further the fourth lecture on simplex, we shall discuss further examples. So not only we shall discuss example with involving simplex, but also some other graphical and formulation exercises we shall discuss in our fourth lecture. All right. So thank you very much, and for the patient hearing, and I hope things are really going in a proper manner.